All right, let's keep going with optimization here. Here we're going to look at a three-dimensional example involving a cylinder. So we'll call this optimization example. Optimization example. Cylinder. And so the tough part of optimization, there are so many factors. You may have to know some geometry, some trigonometry, some algebra. Coming up with the equations initially is often the hardest part. And then you have to differentiate, you have to be able to solve those equations, again, using what you know about algebra and trigonometry or whatever else. And so there's no possible way I can do examples of every type of optimization problem you could ever see. So I'm trying to do several in hopes that you start to get the idea. And then if you need to review your trig or your geometry or whatever other concept you may need to solve an optimization problem, you can go to other resources to research those particular topics. Okay, so the example we're going to have here is asking, what are the dimensions? What are the dimensions of the lightest open top, right right circular cylinder? What are the dimensions of the lightest open top right circular cylinder? Cylindrical, sorry about that, right circular cylindrical can that will hold 1,000 cubic centimeters. What are the dimensions of the lightest open top right circular cylindrical can that will hold 1,000 cubic centimeters? Okay, so this is a great question. What we're going to have to do is draw a picture and kind of talk about what we need to do to solve this. So let's draw a cylinder. So it's got an open top, so it's open up here. It's a right cylinder, just means it's vertical, it's not slanted. And it's circular means it has a circular top and bottom. Okay, so here's our cylinder. When we talk about the dimensions of a cylinder, we need to talk about how wide it is and how tall it is. One way to describe how wide it is maybe in terms of radius. So we'll call the radius of this r. And since r is radius, clearly indicated in this picture, we'll assume it's measured in centimeters, and we'll also assume it's positive. It can't be 0 or negative, okay? The other thing we need to know is how tall this is. So we'll call that height, h, which will also be measured in centimeters, okay? So we have our variables clearly defined by our picture. We could write out in words that r is radius and h is height, but I think it's pretty obvious from our diagram. So now what we need to figure out is a relationship that we know between r and h. So what do we know? In this case, we know that the volume of this open top can should be 1,000 cubic centimeters. So the volume of a right circular cylinder is pretty simple. You find the area of the base. Well, since it's a circle, the area is pi times the radius squared, so that's pi r squared. The area of the base, pi r squared, and then to get volume, you simply multiply that by the height. So we know that the volume of this can has to equal 1,000. Okay? Now, what are we trying to do here? We're trying to find the lightest can. So we're trying to find the lightest can. How do you make a can lighter? Well, you do that by using less material to make it, right? The more metal you use to make this can, the heavier it's going to be. So the The material that you use is dictated by what's called the surface area. How much surface does this have? So in this problem, we want the smallest surface area. And we're assuming that the can will be made of a particular material no matter what. So one sort of clever way to answer this question is, well, just use the lightest material you can find, right? So we'll assume that we've picked our material, and now we just have to decide the size of the can to make it the lightest. So how do we make a 1,000 cubic centimeter can with the least amount of material? Okay? So what we're trying to do here is get the smallest surface area. So what we're trying to do as far as calculus is concerned is minimize the surface area. So we need a formula for the surface area of this can. So we'll call that function for surface area, we'll call it capital A. And there's really two surfaces to this can. We've got the bottom of the can, there's an area that's going to be made from this material. And we already know that the area of the bottom, since it's a circle, is pi r squared. But then we have to add the area of the wall that wraps around the can. Now, that's what we call lateral surface area, the area of the wall that surrounds the inside. And the way to do that is to take the perimeter of this base, which is a circle. So you take the perimeter of that, so that's 2 pi r. You just look at the distance around the base, and you multiply that by the height, and that's going to give you the area of the wall. Okay? So you may want to go, I know I've got a video on this, I may link to it up at the top at this point, but you can also go find other videos on surface area of a cylinder. Anyway, if we had material to create a top also, we would add another pi r squared to get the material to cover the top, but in this case we just have the bottom and the wall. All right, so we're trying to minimize this surface area. And as with every optimization problem, we need the resulting function here to be in terms of one variable. So I need to write all of this with r's or all of it with h's. What I'm going to do is I'm going to opt to replace h with r stuff, because then I only have one h to replace. If I replace the r's, I've got two of them to replace is one thing. The other thing is, I'm going to have to come to this equation and solve for r or for h. Solving for r would require the use of a square root. I want to avoid those if possible, because with my derivatives later, I want to keep the derivative as simple as I can. So I'm going to solve this for h simply by dividing both sides by pi r squared. So h equals 1,000 divided by pi r squared. And now I can come back down here and replace this h with that expression, and my area function will all be in terms of r. So A equals pi r squared plus 2 pi r times 1,000 over pi r squared. Then I'm going to simplify this up a little bit, clean it up a bit, and then we'll move on to the derivative. So when I'm looking at the product here, I can see that the pi's will cancel. And then I just get, and I know I'm going to differentiate, right? So what I'm going to do is I'm going to simplify it, but I'm also going to rewrite it so that it's easy to differentiate. So I've got my pi r squared plus, and then I have 2,000. I failed to mention this. This r cancels with one of those r's. So I've just got 1,000 over r here. All right, so 2 times 1,000 is 2,000 divided by r. That's the same thing as 2,000 times r to the negative first, which is going to be simpler to differentiate. So now I need to look at the derivative of this function. And that should be simple enough. A prime equals Now, one thing to remember is that pi is a coefficient here. It is not a variable, so we don't have to use the product rule. So I'm just going to ignore my pi and do the derivative of r, which is 2r. So this just turns into 2 pi r. The derivative over here turns into negative 2,000 r to the negative second. Okay? So there's my derivative. I need to now find the critical number so that I can try to find the minimum, use this derivative to find the minimum of my area function. So critical numbers tells me that I might want to, because r to the negative second is actually dividing by r squared, this is a fraction. So I might want to combine these with a common denominator to help me find my critical numbers. So that's what I'm going to do up here. So a prime equals 2 pi r minus 2,000 over r squared. You see how we're going back to the division way of looking at it. I temporarily called it r to the negative 1 so I could differentiate. Now that I've differentiated, it might be easier to think of it this way again. If I want a common denominator, I'll have to multiply this by r squared over r squared, giving me 2 pi r cubed over r squared. So I end up with 2 pi r cubed minus 2,000 all over the common denominator, r squared. Let me move to this side. Now I can identify my critical numbers. Okay, so in fact, it may help to factor out a 2 on the top, if you like that. It's always a good idea to factor there if you can. All right, so we have this. Now, if I want this to equal 0, the numerator would have to equal 0. And the denominator would be 0 if r equals 0. However, we already said that since r is radius, we're not interested in an r value of 0 or a negative r value. So we're going to get rid of that. That's not going to be one of our critical numbers. However, we could solve this equation. So add 1,000 and divide by pi. And then take the cube root of both sides. The cube root of 1,000 is just 10. And the cube root of pi is just the cube root of pi. You're welcome to just call this the cube root of 1,000 over pi if you like that. Whatever makes the most sense to you. So this is our critical number. Okay? All right, so I've kind of run out of space here. I'm going to pause the video and clean this up so we can resume the problem with just the information we need. Okay, so I've got our expression for h, I've got our area formula, and I've got our derivative formula along with our critical number. So now what we have to do is look at a prime to help us determine when a is increasing and decreasing. So I'll set up my r variable, my a prime, and my a. So I've only got the one critical number, 10 over the cube root of pi. Remembering that on this side, r has to be greater than 0, but also less than 10 over the cube root of pi. And on this side, r could be anything greater than 10 over the cube root of pi. Then I'll determine the values of a prime at each of those intervals. At the r value, at the critical number, we already know that a prime was 0. So that means a will have a horizontal tangent line. And if you think about numbers less than 10 over the cube root of pi, when you cube that, you'll get something smaller than 1,000 over pi. Multiplying by pi gives you something smaller than 1,000. Something smaller than 1,000 minus 1,000 is negative. Times 2 is negative. Divided by something squared is negative. So any r value over here gives you a negative a prime. And similarly, if you pick a value bigger than 10 over the cube root of pi for r, this guy is going to be bigger than 1,000, so a prime is going to be positive. So smaller than the critical number, a is decreasing since a prime is negative. Here a prime is positive, so a is increasing. And we've got our area function, which is continuous everywhere, and it's decreasing, horizontal tangent line, and increasing. So this will be a minimum for the surface area function. Okay, it's an absolute minimum. There are no others. So this is the smallest. This R value will yield the smallest surface area in this problem. So now let's figure out how to answer the question. The question is, what are the dimensions of this can? So we know that R is 10 over the cube root of pi, and that's measured in centimeters. So that's the smallest, that's the radius we'd want. And then we need to know H. So the dimensions I'm using are the radius and the height. If it were more specific, it may ask for the diameter and the height. Well, we could simply multiply the radius by 2 to get the diameter. Okay, so simple enough. Since it's not specific, I'll be satisfied to give the radius. The height of the can be calculated using this relationship between H and R we saw before. So it's going to be 1,000 over pi times this thing squared, which is 100 over the cube root of pi squared. Okay? And if we simplify that, 1,000 divided by 100 is 10. Dividing by the cube root of pi squared on the bottom is the same as multiplying by the cube root of pi squared on the top. And then on the bottom I have pi. And there's so many ways you could simplify this, right? This is the same thing as pi to the 2/3 power divided by pi to the first power. You could subtract those to get pi to the negative 1/3 power. So we could say 10 times pi to the negative 1/3. And you can see how clean that looks, and that will be centimeters also. Okay? So the dimensions we'd want would be this radius, and we'd want this height. And that would minimize the amount of material we'd use to make this can that holds 1,000 cubic centimeters. Now you may want to give approximations for these values using a calculator so that you can understand what these numbers are a little better. And that's certainly simple enough. Well, let's see here. This is interesting. So I just realized that 10 divided by the cube root of pi is the same thing as 10 times pi to the negative 1/3. So it happens that we would want the radius and the height to be the same measurement. And that may not be something we'd guess if we were trying to reason out the answer to this question. But luckily we can do calculus and we can find out for sure how to minimize the amount of material.